Hi, this is Computational Molecular Science Online again, and I'm Professor Zygmunt. I'd like to show you how you can take experimental data that you've obtained or someone else has obtained, and these are data that you expect should fit some kind of theoretically predicted function. Well, how do you adjust the values of the parameters that are in that function to make the experimental data fit that curve as best as possible? So, here's, again, this is something that's very similar to what I've asked you to do on one of the homework problems, and so I thought I would show an example, slightly different. This actually uses the potential energy function that was employed in the example that I worked out for this week's homework assignment, where the potential energy is expected to follow the form of a constant divided by the interatomic distance squared minus another constant b divided by the interatomic distance. So let's just assume that we have some good reason to think that that function should fit experimental data. But what are the values of the a and the b? And that's our goal. Find the values of a and b that best make that theoretical predicted curve pass through the data points. Well, first, here are the data that are provided. The value of the interatomic distance in these arbitrary units from 1 to 8, and the potential energy at each one of those values. So in Excel is certainly not the only tool that you can use to do this, but if you have access to Excel and if it is convenient for you, then it's a good tool to use. So I'm going to do a scatter plot with those data. I highlight the data, and I'm not going to connect them with curves because my fitting function is going to do that for me. So here's what I have. What I like to do with these kind of plots is right-click on the area out front and move them, give them a name. In this case, I'm going to call it U of R. And what that does is it gives this graph its own sheet and puts it on a tab at the bottom of the Excel spreadsheet. So I can toggle back and forth between the raw data, sheet 1, and the graph. And so here I see potential energy plotted versus the interatomic distance. And it does have that same kind of form where it starts off at low values of R, very high, and comes down and has some sort of minimum and then increases as we go off toward large values of R. So let me do one thing as I go to the layout, the chart tools layout. Do I want the design? Select data. And let me just use that series 1, and I'm going to edit it because I want to give it a name. I don't want to just call it series 1. I'm going to just write down EXPT, experiment. So then those data will be labeled as experimental data. So what I showed you on the homework assignment is that there's a website where you can take data points and then define a fitting function and then get the best fit. And so here is that web page, statpages.org, and I gave you the full link in the homework assignment. There's a lot of background information about what is nonlinear curve fitting, but let's just cut to the chase and go to the instructions. Basically what you need to do is enter the number of data points, and this example has 8. The number of independent variables, well, in this case the independent variable is the interatomic distance. There's only one of them. The number of parameters, which is the number of constants that we have in our expression, and then we have to enter a formula for the function. And this program, this website, uses y and x. In fact, the symbols for our data are u and r, but that's okay. We'll just use y and x and follow their syntax. So what I need to do is write down a, and then I have to divide by r squared. In this case, I'm going to use x. And you might think that you could use the same kind of syntax that a program like Excel accepts and use x caret 2 to represent x squared. Well, it doesn't work that way with this program. If you look at the instructions down at the bottom, the way that it does powers, if we scroll all the way down, syntax, okay, if it does, where can I, power, algebraic, power x comma y, that's how it defines x raised to the y power. So if I want to indicate x squared in my function, what I have to do is write down power x comma 2, like that. So that is a over x squared. and then I want to subtract b over x, because that's the way, if I go back to my spreadsheet, that's the functional form, a over r squared minus b over r. So the only difference is that I have an x instead of an r. So that's the way of writing down that function. Now it has a bunch of sample data that are here on the website, so we want to delete all those. And what's very nice is that these data from Excel that I've highlighted, we can copy those and paste those into here, and it automatically takes care of the formatting. So the x values have to come first, the y values come second, and so then we can scroll down to the next step, which is to enter your best guesses for the parameters. That's a little bit hard to do. If we go back and look at the graph, what would be guesses as to the values of A and B? It's a little bit difficult looking at the graph. Well, I suppose that what I could do is look at this point here, which is 1, 2. And if I assume that the at that value of r, that small value of r, that the negative term is somewhat negligible, so that only the positive term makes a significant contribution, what would the value of a be that would give me a point where r is equal to 1 and u is equal to 2? And so that would simply be 2. So I might guess that that value for a would be 2. And so a is the first value here, so I just plug in 2. That's probably not very close, but I can at least try it and see if the program will find the best fit using that data, or that value. Now what about the b parameter? Well, let me go to the opposite extreme. If I go back to my graph, at a value of r equals to 8, the u value was about -1/2. All right, so let's look at the form of the function here. So if I want -1/2 and r is equal to 8, then b would be about equal to 4, wouldn't it? -1/2. So let's try putting in a 4 value, 2 and 4. Then all the other parameters it shows here, this program can do any kind of fitting function up to 9 parameters. So all the other ones we have to leave blank. So now I've filled in the information that's required, and now we click the iterate button, because this program solves, it does the fitting iteratively. It does one pass, okay, and you can see after that first pass the values it got for A and B, 7.9 and 5.9, and this next box represents an uncertainty. There's a plus or a minus. Every fit has some kind of uncertainty that's been introduced. So those uncertainties are pretty large compared to the values of the function, but we're not done, because what we have to do, as it says, to keep clicking the iterate button until the parameters don't change anymore. So if I click it again, okay, they changed a little bit, the errors did. If I click it again a couple more times, nothing's changing. So I'm done. I've got the best possible fit of that function to those data points. So this is my value for A, and I'm going to copy that value with Control-C and paste it into the spreadsheet in the box I've reserved for A, and then do the same thing for B. Here's my value for B. I'm going to copy it. I'm going to paste it into the spreadsheet. Voila. So there are my values for A and B. But how do I know whether that's a good fit? Well, you always have to display the fitting line on top of the data points. But to display the fitting line in Excel, there's no simple automatic way to do it, so I'm going to calculate another column of data for our values from 1 to 8. I've already created a column here, and then use the equation to create a column of fit values. And then I'll make that plot on top of the data points. So here, right here in this cell, I've got to put equals, because that tells Excel this is a formula. And A, the value of A is B6, cell B6. And I'm going to put $B, $6, because when I paste this value down into the lower values, I do not want it to change. So it's $B, $6 represents cell B6, and I want to divide by the R value, which is this value here, squared. Now, Excel does allow me to use the caret. So D10 is the value of R. Here it's equal to 1. So then I have to subtract $B, $7. Whoops. I'm going to make errors sometimes. Okay, $B, $7, because B7 is the B value, and that I want to divide by R again. So it's D10. So I hit enter, and I get a value 1.99, very close to the 2 that was the experimental value. The beauty of using those dollar signs around the B6 and the B7 cells is now I can do a Control-C and copy that and paste it all the way down into all of the other points. And you wonder, well, why did I choose increments of 0.2? Well, I didn't want to make this too long, and it seemed like a reasonable number of points that I can now display as a line on top of the experimental data points. So now I'm going to go back to my graph here, and now what I need to do is go to layout, go to design, sorry, select data, and now I want to add a data series. All right, the series name is going to be called the fit, and then the X values here, I click in the X value box, I go back to the sheet, the X values are the R values. So I highlight all of those from 1 to 8. Then the Y values, I clear this out, I go back to the sheet, and I highlight all the Y values, which in this case are the potential energy values, making sure that the cell values make sense. The X values run from D10 to D45, the Y values run from E10 to E45. Those should match up. And if they do, I click OK. All right, and then what I can see is I've got a second set of data superimposed on the first. Now this isn't very aesthetically pleasing because I'd like to have data points for the experimental data and a line for the fit. So if I right-click and then click Format Data Series on the fitting line, then I can go to marker options and I can turn off the markers, but then I can go to line and I can put solid line. And then click close, and what the program has done for me now is superimpose the line that represents the fit data, the fitting function, and left the data points that were the original experimental data. All right, so this is how you can use this website to perform a fit of a specific kind of function that you tell the program what function you want to use, and then you fill in the blanks with the individual number of data points and parameters and so on, type or paste in the data, and then you get your fit that shows the best fit of those parameters to those experimental data. So you should be able to do this without too much trouble for the data that I have given you for the homework assignment. Contact me if you have any questions. Good luck.